So in the last lecture, we showed that the standard model does not satisfy some of the Sakharov conditions. We discussed that baryon number is and lepton number is violated in the standard model, which is good, but the other two Sakharov conditions are not satisfied well. So the second one is CP violation. We discussed that even though there is CP violation in the standard model in the CKM matrix, this CP violation is not enough to generate a baryon asymmetry. The baryon asymmetry it would be able to generate is 10 orders of magnitude smaller than what you would need. And the third condition of thermal inequilibrium is not satisfied in the standard model at the temperature regime that we wanted to. I feel like there's an echo or some like ringing or something. Okay, so since standard model does not satisfy these conditions, especially the last two, the second and third condition, we need to have some new physics, and this new physics should come with definitely some extra CP violation and a process that is not in equilibrium in the early universe, and this new physics has to talk to the standard model, right? Because at the end, we want to produce our baryons and our leptons. The first condition, since it's satisfied in the standard model, this is your choice as a model builder if you are going to rely on the standard model baryon number violation, or if you will come with a new process that violates baryon or lepton number. Okay, so this depends on the model builder's choice, basically. The set of models that rely on the standard model sphalerons are called electroweak baryogenesis, which we will talk about in the next lecture tomorrow. And but again, you don't need to rely on that. And a set of models, or really a large class of mechanisms that doesn't rely on sphalerons, is basically just models that have some particle that decays what is called out of equilibrium. So I will start with not leptogenesis, but basically a more general mechanism, which is just baryogenesis from particle decays. And Leptogenesis is an example of such a model. This is a very straightforward case. This is where I'm starting with creating the baryon asymmetry from particle decays. So for this generic model, let's just consider a complex scalar. It will have decays like this. This complex scalar can decay to a pair of two quarks, QQ, and a Q bar and some state X. Okay, this is what I'm requiring from my model. So of course, since it decays to a QQ, S needs to be a color triplet or a sextet, right? So the baryon number of this state is 2/3, because each quark has baryon number 1/3. And I'm requiring that this state has baryon number 0 and lepton number 0. So this final state has baryon number -1/3. So since S decays to a final state with baryon number 2/3 and baryon number -1/3, it's not possible to assign a baryon number to S in a way that this will conserve, one of these decays would conserve, or both of these decays would conserve baryon number. So S decays will definitely violate B, right? Okay. These kind of decays and mechanisms were very popular, especially in grand unified theories. In grand unified theory, you would want basically all fermions to have come from a nice unified model. So you would put both baryons and leptons into the same multiplet at some point, or in the before you break the unified group. Then there would be some scalar that could decay to both baryons and leptons. And it's like not hard to get baryon and lepton number violating decays in these kind of models. Of course, if you are breaking both baryon and lepton number, so here I'm only breaking baryon number, which is good because I don't want my proton to decay. If you only break baryon number, proton will still be stable. If you break both baryon and lepton number, you need to make sure that your proton doesn't decay. Well, let's just think about the baryon number so far. And then when we do leptogenesis, we will use lepton number violation. So these are the decays of this particle S. Of course, there is also the complex conjugate of this, because my scalar is complex. So S bar will decay to Q bar, and also QX, or QX bar. Could have other. I will call, so the decay, the widths, the partial widths of each of these decays are important, and let me just define my notation real quick. So the partial width for this decay I will call, what do I call it? Gamma 1. This one I will call gamma 1 bar. And this one I will call gamma 2 bar. So CPT invariance dictates that the total width of the S and S bar are the same. Okay, so these are the same, the total width. And if there is CP violation, this just means that gamma 1 is not equal to gamma 1 bar, and gamma 2 is not equal to gamma 2 bar. And again, I want to stress that baryon number violation on its own is not enough to produce a baryon asymmetry, right? Even if you had decays that are baryon number violating, the same happens for the conjugate decays as well. And if you start from a baryon symmetric universe, or if you start from a universe that has both S and S bar at the same, with the same number density, basically, you would just produce plus B and minus B, but on average, you wouldn't end up producing a baryon asymmetry, right? So you definitely need CP violation so that one of these decays is favored, basically. And here, well, it's not too important for this specific case, but it's usually, when you have models like this, from particle decays, it is best to keep track of not just baryon or lepton number, but actually the B minus L number. Of course, none of these things have lepton number, so B minus L number and the B number is the same, but this is because sphalerons conserve B minus L. So, of course, in the universe, it's not only these things that exist, standard model exists as well, and the standard model sphalerons would be active as well. Well, at least in the temperatures that will be relevant for this case. So it's best to keep track of B minus L number because sphalerons will conserve this. So if you create a B minus L number, it will be conserved at the end of when the sphalerons turn off as well. But again, for this case, it is they will be equivalent. So we can define the asymmetry that will be, so let's define the, actually I need more space. So I can almost reach the top of these bars. I will call this delta. Delta is equal to so this decay gives me a 2/3 baryon number, and this decay gives me a minus a third baryon number, and then minus the decays of S bar. Again, if gamma 1 is equal to gamma 1 bar and gamma 2 is equal to gamma 2 bar, you wouldn't have any CP violation, so there won't be an asymmetry. So if CP is conserved, delta is 0. As you would expect. And you can exchange gamma 2 for gamma total minus gamma 1, and similarly for gamma 2 bar. So using CPT invariance, you can write that. Okay, so this will be our measure of CP violation, basically. Now, what you will do next is, of course, just calculate these decay widths given your Lagrangian. It's actually, okay, so the first thing you would do is basically try to calculate this. Yes?
Why is there no term with gamma 2s in the delta?
Sorry, what? Oh, yeah, no, I just exchanged gamma 2 for gamma total minus 1 and gamma 2 bar for gamma total minus gamma 1 bar. So, yeah. Very good. Yeah, so next thing you would do to calculate the baryon asymmetry is calculate these partial decay widths and the total decay width of the particle. And of course, the first thing you would do is calculate it at 3 level. But at 3 level, actually, there is no asymmetry, and this is very easy to see. So let's just draw a diagram. So this is S decaying to QQ, and then you will need S bar decaying to Q bar, Q bar. Let's say there's some coefficient here, G1, and this one is the CP conjugate, so this will be G1 star, right? So this is this versus this diagram. And of course, at 3 level, so this one will be proportional to the absolute value square of G1. And then this one will be proportional to the absolute value of G1 star squared, which is the same as G1 squared, absolute value squared. Right? So this is to say, there's no CP violation at 3 level. This seems like a very obvious thing to observe, but it has quite important consequences for model building. And it also kind of immediately tells you that to see the effects of CP violation, you need to go to the loop level. So you expect that you will have some loop factors that will suppress your asymmetry, which happens, we will see happens at Leptogenesis models as well. And even going to the loop level isn't enough. You actually need another state to decay to the same final states. Another state or another coupling. For example, in another scalar that decays to the same states by going to Q bar X. And then you need to go to loop level as QQ. So there's a G1 here. And then the first, this is enough. So there's going to be an S. X. So this is G2. This is S prime. Okay. And this is F's are these ones. And then this G2 is the S to Q bar X decays. So now this loop decay and loop diagram interferes with the tree-level diagram. And only at this level that you will see CP violation. One of your exercise questions is calculating this for the Leptogenesis case. I won't calculate it here, of course. I will just write the dependence on the coupling constants. You can see, so gamma 1 will have some loop integrals, sorry, some coefficients. So there will be there will be G1. So this is from the tree level. Plus there will be some loop factors. And then the second thing is G2, F2, F1, F2 star. And then gamma 1 bar will have right, so it's the same thing. If you didn't have this tree level, of course, you would only have G1 absolute value square and G1 star absolute value square, which are the same. But when you expand this absolute value square, there will be terms that basically give you the interference between the tree level and loop level. And they will be different by a phase between these two diagrams. Right? So you see the phase difference. And then if you take gamma 1 minus gamma 1 bar over gamma total, now delta will be minus 2. Delta will be proportional to the imaginary part of this interference term. So you will have G1, G2 star, and F1 star, F2, over the total width will be proportional to G1 square, or will be about G1 square plus GT square. Maybe take this. Okay, so this basically is the important part, right? So the CP violation is only proportional to the phase difference between these coefficients. And you can see if you didn't have these ones, if you only had the S states, then you would have a G1 star G2 here, and again, you would not have CP violation because it will be an absolute value again. So this is why you need the second state as well. So this is so we already imposed baryon number violation by just, kind of, right, yes.
Really stupid question.
Yes.
But isn't there another loop diagram that is contributed by SQQ with an exchange of an S prime?
Sorry, say this again?
Should there also be on the triangle diagram? But except instead of having Q bar and X, you have QQ.
Sorry, which one? QQ? Yeah, here.
No, that's the propagators of the loop. Because you can have QQ, S prime, QQ, S prime, vortex, right?
Yeah, you can add that as well. That's fine. Okay. Sorry, yeah. We will do this a bit more carefully when we do leptogenesis. All right, where was I? Oh, yes. So we imposed baryon number violation by just, basically picking our model this way, and CPU violation by requiring that we have some complex couplings with a phase difference. And again, there's only kind of one important or one relevant phase difference, right, between all these terms. And one thing is that, so there's 4 couplings here and 2 here, so this will go like coupling square over probably 4 pi with some loop integral that depends on the mass of the particles that are in the loop. Sorry, ms over ms prime. And the next thing on our list for baryogenesis is satisfying the third condition, thermal inequilibrium. And again, for baryogenesis through particle decays, this is a requirement on the mass of the lifetime of the particle, basically. So we can, okay, this has actually a lot of assumptions. Let's assume that this is my temperature line. This is T equals 0 now, and some very high temperature. And at some point, the temperature is at the scale of these particles, ms and ms prime. I will assume that at temperatures much higher than the particle's mass, these particles are in equilibrium. So this is being in equilibrium means that they will have equilibrium thermal distributions, right? So if it's a scalar, it will have a Bose-Einstein distribution or Fermi-Dirac distribution. So given your model, you need to technically check this, right? Your particles should have large enough couplings that they would have been produced in equilibrium. As you might have learned in your dark matter classes, this is not necessarily always the case, right? You could have weakly interacting particles that were so weakly interacting that they never reached equilibrium number densities, so that you are produced out of equilibrium and maybe you freeze out of equilibrium, basically. There are baryogenesis models like this as well, but this is the easiest case, basically. You just require that particles were in equilibrium and you know their number densities, right? And this requires large or healthy . And again, there can be scattering processes, annihilation processes, pair production processes. So, given your model's Lagrangian, there will be a lot of processes that allow you to be produced in equilibrium. And then below the particle's mass, when the universe's temperature drops below the particle mass, we will assume that the only relevant interactions are particles decays. So everything else will freeze out. This also means that we will assume that the inverse decays stop. So this is S can decay to QQ, but this stopped basically below the particle's mass. Again, these conditions also need to be checked in a model. And this is not absolutely necessary. I will come to this at the end, but it's just a nice simplifying scenario. A very easy or straightforward observation is that for particle decays to be relevant, your particles should live long enough so that they can decay basically when the temperature drops below their mass. So this statement intrinsically assumes that I just saw yesterday that the red doesn't show up really well, so it's hard to see the red chalk. So this is basically to say that the S and S prime particles should live long enough So this is a very nice estimate for the third condition, basically. If the total lifetime of the S particles are long enough, so lifetime is 1 over gamma, so if their width is small enough that they will be around when the temperature drops below their mass so that they can decay. And this, you just basically compare the decay width to the Hubble rate, right? Or the lifetime to the Hubble time. And in a radiation-dominated universe, this is just this. And let's say gamma total goes like g squared over 4 pi times the mass of the particles, of course. This is, I'm assuming all the coupling constants are about the same size, basically. This then tells me MS should be larger than square pi and Planck star. If you want to get some numbers, let's take this to be about 10 to the minus 2. Of course, this is whatever your model is, but just to get some idea, then MS will need to be greater than 10 to the 16 GeV. And this scale, a bit lower than this scale, will come up for leptogenesis models as well. This is actually not too great because, of course, we started assuming that the S particles were in equilibrium at higher temperatures. So that also means that the temperature of the universe should have been greater than this at some point, so that they would have been produced in equilibrium. And that sometimes becomes a problem for your model as well. But it's still not undoable. All right, so far so good. It's the easy parts. And I want to emphasize that you don't need to produce the S particles in equilibrium for a successful baryogenesis models. This is just easier. This version is the easiest to do analytically. Okay, so let's go with these parameters and estimate the baryon symmetry. Okay. So if the S particles were in equilibrium here, right, their number density. Oh, sorry, let me just draw this here. So their number density will go like T cube, and more specifically, it will be GS, the degrees of freedom of the S particle, this pi square over times T cube. This is about 1.2. So the B minus L asymmetry is just equal to this coefficient delta, or proportional to this coefficient delta, times how many S particles you have. And here my notation is getting a bit confusing, but this is the entropy density of the universe. And so this go like, so NS is about T cube over pi square. I'm assuming GS is some order 1 number. And then the entropy density is 45 over G star S 2 pi square T cube. Right? And this is about 0.1 delta over G star. Again, G star is the number of relativistic degrees of freedom that contribute to entropy. And if we take G star to be about 100, this is delta times 10 to the minus 3. Again, given your model, you need to calculate G star, but this is the standard model is about 100 at high temperatures. So this is telling us that, and we know the Baryogenesis symmetry that we need is 10 to the minus 10. And you see this is delta times 10 to the minus 3. So this tells you how much CP violation you need, basically. So in order to produce the observed Baryogenesis symmetry, then you need delta of about 10 to the minus 7. Right, it's not too large a number. And if we go back to, I was going to keep this. Sorry. So remember what this was. This is larger than G squared. So let's now remember our little estimate for what delta was in this model. Delta was G squared over 4 pi times some loop function. Right? So we want this to be about 10 to the minus 7. So we want this to be about 10 to the minus 7. So I'm going to require that this means G squared over 4 pi is order 10 to the 7. And then if you use this estimate for this, then you get MS needs to be greater than 10 to the 10. So it's a bit better, right? Because we don't need too much CP violation. That means we can kind of live with smaller coupling constants. That also tells us that our particle that's decaying needs to be heavier than 10 to the 10 GeV or so. It's kind of easier than 10 to the 16. Now the universe needs to be just hotter than 10 to the 10 GeV. Questions? So if you were doing this more carefully, you would, of course, set up a set of Boltzmann equations to calculate the Baryon symmetry. So you would look at, and this is important for, again, making sure that the S particles are produced in equilibrium or not produced in equilibrium as well, right? So you would basically need to solve for the change in the number density of each quark, which will be relevant because your S particles can decay into quarks, but also you could be destroying a quark asymmetry because your quarks are decaying back to S particles as well. And then you would do the same thing for, and then there's going to be S prime too, right? S prime processes. And you would need to set up the same equations for, and then the universe's expansion. And then, of course, the universe is expanding. And then you would need to set up the same equations for antiquarks. And what you want to find is the difference between them. When you set up the Boltzmann, yes? This one is a minus sign. Yeah. Very good, thank you. And when you set up the Boltzmann equations, we will write this for Leptogenesis, you will see that the gamma 1 minus gamma 1 bar, these kind of differences will come up here anyway, right? So you will see that the S going to QQ and S bar going to QQ bar will be the same. So you will be able to see basically the same delta coefficient in a way. Where was I going with this? Yeah, so. And again, when you do the correct Boltzmann equation calculation, at some point you can see that these rates are always compared to the Hubble expansion of the universe. This is similar to, again, how dark matter freezes out, basically. Dark matter annihilations freeze out. But you can compare everything to the Hubble expansion rate, and at some point your asymmetry production can freeze out. So if this is A, you can produce some asymmetry, and then this is delta B minus L. This is kind of time or the scale factor. And then here your particles will be decaying. And then this is the Baryon symmetry that you end up with. Now, you don't need to be in this very nice parameter place where you only decay out of equilibrium. You can actually live with a bit of what is called washout. So if your particle decays are still kind of in equilibrium below the particle's mass, then what happens is that you basically wash out a bit of the asymmetry maybe. This is because of inequilibrium decays. But this is not the worst thing to happen, because we picked our parameters to exactly produce the Baryon symmetry, but you could produce a bit extra and then live with some washout. Okay? So if you're, again, model building, if you have washout, you don't need to freak out. You can always produce extra asymmetry and then allow for some washout. Baryon symmetry is not too large, right? It's 10 to the minus 10. So say if you produced some order 1 or maybe order 10 to the minus 3 asymmetry, you could live with some entropy dump, for example. Again, I was going to say this as well. So another thing that when you are working on a model, of course, it's very important to, I kind of assume entropy here is there's no entropy dump, basically. Entropy in a co-moving volume is conserved. That's why we can just like write it like this. But if you have other particles in your model that decay later, for example, and then they could be producing a lot of entropy, and this could dilute your asymmetry as well. So you need to be sure that there's no entropy dump later in the history of the universe, so that you don't dilute the asymmetry that you produce. Or again, you could be producing larger than necessary asymmetry, and then you dilute some of it. But this you always need to check. Okay, so this is a good point to, I think, take a few minute break to stretch our legs, and then in the second half of the lecture, we will talk about leptogenesis. All right, so we are finally coming to the actual title. Sorry, oh yeah, wait, I need to turn on. Yeah, so we are finally coming to one of the titles of these lectures, which is leptogenesis. So this is like really one of the most popular ways to explain the baryon asymmetry, and it's a model again that relies on the out of equilibrium decay of some heavy particles, and in this case, it's a heavy Majorana neutrino. So you already saw this kind of Lagrangian. This is like a seesaw mechanism, including 2 or more heavy Majorana neutrinos. So I will add alpha C H bar star. These are the lepton doublets, and then alpha counts the heavy neutrinos, and then these have Majorana masses. And alpha. Of course, the Majorana mass terms violate lepton number. So this is but also they violate B minus L as well. Right, again, you learned this in the neutrino lectures. This is a very nice way to explain why our neutrinos are massive. And the neutrino masses, the light neutrino masses that we observe will be proportional to the 1 over this Majorana mass. So if you want to get neutrino masses of order EV or so, you require a seesaw scale or a heavy Majorana mass of 10 to the 16 GeV, right? So this is the easiest vanilla leptogenesis scenario with like a type 1 seesaw mechanism. It's also almost a similar scale as what we would expect from a particle that decays to produce the particle asymmetry. So for the Leptogenesis scenario, and this the terminology baryogenesis versus Leptogenesis, so baryogenesis technically is used almost exclusively for electroweak baryogenesis, but more inclusively for producing directly the baryon asymmetry, like a particle that decays directly to a baryon asymmetry, versus leptogenesis, where you produce a lepton asymmetry, and then we will also see that this lepton asymmetry is partially turned into a baryon asymmetry by sphalerons. Okay, so this is the two different schemes. All right. So for leptogenesis, we will focus on the lightest of these. So I'm assuming a mass hierarchy where M1 is smaller than, well, it doesn't have to be much, but let's say M1 is smaller than M2, 3. So we will assume some mass hierarchy. For leptogenesis, we will focus on the decays of the lightest one. So N1 can decay into some lepton, wait, I call these. And also, of course, the conjugate state. Okay, so we will focus on these decays, but technically so these are not the only lepton number violating interactions. You can also have lepton number violating scatterings. For example, right? This is the same interaction basically. We'll facilitate this as well. We will ignore these here. But they can be relevant and they should be included in a more careful calculation. Yes, some of you were asking me about assumptions and stuff in baryogenesis calculations at breakfast. And again, this is a very big assumption that I'm making right now. Right, so this is not too different than our toy model, right? In our toy model, we assume the baryon number violating decays, but here's just lepton number violating. Calculations are very similar, and it's also exactly the case that at 3 level, the CP violation CP violating effects will not show up basically. And again, for CP violation to exist here, we have to have complex coupling. So this Y alpha are complex. Okay. And here we already have 2 or more states that decay into the same final state. So we have N1, N2, N3, right? So this will be the equivalent to S and S prime basically. And we have 3 of them. And again, at 3 level, there's no CP violation for the same reason. So if you look at this, this is Y1 alpha. So at 3 level, if you just look at the width of this, it's going to be absolute value Y1 square. And then if you look at the complex conjugate process, it will be the absolute value Y1 square again. So there's no CP violation. So you need to include loop diagrams. And there's actually 2 in this case that we need to include. This is and one. Let me write my couplings. So this is Y1 beta star. This is Yj alpha, and then this is Yj beta. And there's another one. Did not leave myself enough space. So there's this one. Okay. Right, so now this 3-level diagram can interfere with the loop diagrams. And of course, we will need to know the partial width of this process and the conjugate process. So this will be equal to some constant y1 alpha plus. Now in the loop, there can be n2, n1, n2, n3, and then this beta can be e mu tau, right? So there will be a sum over j and beta. There will be some loop function that depends on I'm assuming the leptons are massless, that will depend on the mass of m1 and mj, and then y1 beta star j alpha j beta, absolutely, sorry. Sorry, not m2, mj. Right, and the CP violation will be defined as n1 decaying into this state with some lepton number 1 minus n1 decaying into the other state over the total width of my particle. The total width is, you can just estimate this. Right, just a two-body decay. Now, again, when calculating this difference with the complex conjugate part, you will be you will have a term that is this loop function minus its complex conjugate, and I'm just going to write it as some function f. Okay, now, so plugging both this and this reparameterization into delta, you can write the CP violation as 1 over 8 pi this function. Sorry, I just need to keep track of my notation. Having an n1 in the loop doesn't contribute, because if you had 1 here, again, you don't get a phase difference, right? You would only get an absolute value, which is why we included an S prime particle in our first calculation. And so far, I'm only keeping track of the coupling constants and like, which coupling constants contribute and stuff. And of course, the one thing that you need to calculate is this loop function. And for if M1 is much lighter than M2 and 3, this thing is M1 over Mj. I'm going to put this back in here. This is from the total width of my of the lightest heavy neutrino, or lightest right-handed neutrino. Okay, 2, 3. And I'm writing this part in just a slightly different way because we can see how it is related to the neutrino masses this way. J alpha star. Okay. Again, this is the same thing here. I just wrote it in a suggestive way because this combination is related to the neutrino masses, right? The lightest neutrino masses. So the light neutrino masses go like the Yukawa couplings over the right-handed neutrino mass. So this combination is actually directly related to the light neutrino masses we can measure, which gives us an idea of how big this thing needs to be, basically. So if you remember, so two things to actually to say. So if you remember the combination of the Yukawa couplings that goes into the neutrino mass matrix, you have something like this, right? Over 2 J alpha Mj Yj beta. So this is not exactly this. Right? They're not exactly the same, they're very similar, but also this is to say that so I'm going to claim that the PMNS matrix is not directly related to the Baryon symmetry. Yes? Sorry, which one? This is imaginary, sorry. Yeah, imaginary. So if you listen to a lot of Dune or Hyper-K talks, these two experiments, among other things, they are trying to measure the CP violation in the neutrino sector, so delta CP in the PMNS. But even if they measured non-zero delta CP, and even if that CP violation is quite large, that CP violation doesn't really directly feed into the CP violation that's necessary for leptogenesis. You will still need some extra CP violation in the right-hand neutrino sector, basically. So your PMNS would be a larger matrix, and you will still need the CP violation in this coming from the right-hand neutrinos. Okay. I know of only one model that uses the CP violation in the PMNS, but still needs extra. I will try to find that paper and include it in my lecture notes. So this is this is not a lecture, right? The lecture ending. Okay, very good. It's like, is it the bell for lunch? So still, like, even if this is, but. It will still be interesting to know that there is CP violation in the neutrino sector, but again, it's the same problem. Like, there's CP violation in the CKM matrix in the quark sector, but that's really not relevant for the Baryogenesis symmetry. Even if you were doing baryogenesis, you still need extra CP violation. Same thing happens for leptogenesis as well. Even if you had CP violation in the neutrino mixing matrix in the PMNS matrix, that's still not enough for, not relevant for leptogenesis. You still need extra CP violation. So you cannot really, you cannot play around with this. And the same for theta bar as well. Even if theta bar was, even if we had a theta bar GG dual term in the standard model, that's also not relevant for baryogenesis. So you still need some new physics with CP violation. So it seems like standard model, even when you include the non-standard cases to explain neutrino masses, CP violation is really not enough to generate the correct Baryogenesis symmetry. So this is one thing, and the other thing is, so yeah, and the other thing is, I don't have it in my notes, but okay, so one other thing that, of course, the neutrino experiments are looking for is the neutrinoless double beta decay. And this would show that neutrinos are, if neutrinos are Majorana or Dirac, right? And again, which is important for knowing if there is lepton number violation in the standard model itself. Even if you knew that neutrinos are Majorana and then there's lepton number violation, again, this is not directly related to leptogenesis itself, leptogenesis models. For any leptogenesis model, you need some heavy right-hand neutrinos which come with their own lepton number violation and CP violation as well. So unfortunately, the low energy neutrino experiments are I don't think they will tell us anything about the exact the correct leptogenesis model we have. It would be interesting if neutrinos were Majorana, because they will be the only Majorana particles that we have. So that will be interesting on its own, but not relevant for leptogenesis models. And the combination of parameters that go to the neutrinos double beta decay rate, so it's the MEE usually, that's again not relevant for the Baryogenesis symmetry. So it's a different combination of the Yukawa couplings that doesn't directly relate to the Baryogenesis symmetry, unfortunately. All right, very good. So okay, so let's do again, very rough estimate of the Yukawa couplings or the masses that we will need to get the correct Baryogenesis symmetry. So this is, again, saying that CP violation, you get CP violation if you have complex Yukawa couplings for the right-hand neutrinos. And then you, of course, need to have several of them, and you look at the phase difference. And the lepton number violation coming from the fact that these are Majorana, so there's lepton number violation. The only thing that's left is the out of equilibrium conditions. And again, for the out of equilibrium condition, we require that the width of the particle, width of the lightest neutrino is smaller than the Hubble rate at the temperature that equals its mass. And this gives us an idea. So the width is 1/8 pi. This is again just requiring that the neutrino lives long enough that the temperature drops below its mass. And then we are assuming that at that temperature, the inverse decays and other interactions are frozen out. So the only relevant thing is the decay of the particle. Again, this is an assumption. You, of course, need to calculate this. But with this assumption, and this is the most, again, the easiest or the first version of the leptogenesis models. This is m1 squared over m Planck. And one thing we can say is that, let me define this. So this is basically the total and one contribution to the neutrino mass matrix. So this needs to be much, much smaller than 4 pi v squared over m Planck star. I just took 1/m1 here. That's why there's a capital M1 here. Right. And this side is 10 to the minus 3 electron volts. Oh wait, does the lecture end at 10:30 or 10? No, 10:30, yeah. Now this contribution is, oh wait. I can write this as y1 theta. I'm assuming that you saw all these neutrino mass matrix elements in the first week, but I'm just rewriting stuff so that I can relate them to the neutrino mass measurements somewhat. Okay, so now we can assume normal hierarchy where M1 is much, much smaller than M2, which is about the solar, and then smaller than M3, which is the atmospheric mass difference. And the atmospheric mass difference is about 0.05 electron volts. Coming back to my delta, okay, so, and then if you remember my delta, the asymmetry for a particle decay went like delta, the CP violation over G star. This was assuming that the particles that are decaying, the N1 particles, are in equilibrium at high temperature, so their number density is about T cubed, and then the number density times delta over the entropy density of the universe gives you about this rough estimate, basically, CP evaluation over G star, and assuming G star is about 100, you will get, and then we want this to be 10 to the minus 10. If G star is about 100, delta needs to be 10 to the minus 8. So comparing these two, this then tells me that if delta is 10 to the minus 8, this is 10 to the minus 2 electron volts, and then doing all of the other things, you will get M1 needs to be greater than 10 to the 9 GeV. Okay, so this is kind of a similar scale that we expected from just a particle decay, right? 10 to the 10 or so. And of course, you also need to just go from the lepton asymmetry to the baryon asymmetry, and you will do this calculation. Maybe you already did this calculation. So this is the lepton asymmetry, and of course, this lepton asymmetry, okay, so I said here 10 to the minus 10, but this is not quite correct, right? Because what we measure as 10 to the minus 10 is the baryon asymmetry, not the lepton asymmetry. And going from the baryon asymmetry to lepton asymmetry is a nice calculation, but you can say that the baryon asymmetry is related to the B minus L asymmetry, actually, and the conversion is like this. Plus 4 number of scalar doublets. Right? So in a leptogenesis scenario, what you produce is a lepton asymmetry or a B minus L asymmetry. And what we measure from BBN and CMB is a B asymmetry. And for a given B minus L, this is how much baryon asymmetry that you will end up with after sphalerons wash out some of them. This is the number of fermions you have, and this is the number of SU2 doublet scalars, so the Higgs doublets basically. And for standard model, NF is 3. So 3 generations of fermions, and number of fermion generations, and NS is 1. So for the standard model, this is 28 over 79 B minus L. So it's about a third. And this is just to say that you need to produce 3 times the baryon asymmetry in lepton asymmetry, because some of it is going to be washed out as B plus L, and this will be the remaining baryon asymmetry. So for leptogenesis, you need to be careful that you are producing enough lepton asymmetry to begin with to end up with the correct baryon asymmetry that we have. If you have a different model, of course, you need to be careful. For example, if you were in a SUSY model, then you would have 2 Higgs doublets, right? So you need to account for that. And for a given model, you need to make sure that you have the correct conversion. Are you guys finished with this calculation for the problem sessions? No. There's getting to this point. This is requiring that. Okay, so you need to follow a set of detailed balance equations, making sure that in each standard model interaction, the hypercharge and other conserved charges are conserved at temperatures that are relevant. So when you are doing this detailed balance, you are basically making sure that chemical potentials on each side of the interaction balance with each other. And when you go through all the calculations, and in the problem set, I gave you a very simplified version of this, which works perfectly, so this is fine. So when you're making sure that, for example, in a weak interaction, electron-positron scattering going to something else, or the chemical potentials are conserved, you end up relating a B minus L asymmetry to a B asymmetry. This is because the chemical potential of B minus L needs to be conserved, basically, in thermal equilibrium. So you do this you do this detailed balance calculations, and this part is not too hard to get. So in the problem sets, I told you to only think about the B minus L charge and the hypercharge. Again, this is enough. Technically, of course, all of the standard model particles are charged under other things as well, and you can include those two, and then at the end you will see that they don't matter. It's only the hypercharge and B minus L, which is kind of fun. But if you have a new physics model, and especially your new physics model come with extra gauge groups, then you need to make sure that you are redoing this calculation to find the correct conversion. So this won't be the same this conversion holds basically with just this standard model gauge group, right? And then you can say, you can add, with the standard model gauge groups, you can add extra doublets and extra generational fermions, is fine. But if you are adding extra gauge groups, you need to be careful and you need to redo the rebalancing again. There's actually, there are works that do this for generic groups like SUN with generic number of fermions and stuff, and there's a ton of detailed balancing that you need to do, but these are calculated, so you can also look up those tables as well, which is fun. Anyway, I hadn't done this calculation when I was in grad school, so I wanted you guys to do it just to see where these numbers come from. All right, questions? Before lunch. We are almost at lunchtime. Okay. So this was a very rough estimate, or very rough like sketching basically. But again, for leptogenesis, so basically leptogenesis works because it both explains the neutrino masses, and again, when you are trying to explain the neutrino masses, one of your neutrinos end up being long-lived enough that it can decay out of equilibrium, and if it is heavy enough, it also can give you enough CP violation to produce lepton symmetry. So this is beautiful, really. And this 10 to the 9, there's another limit, so it needs to be around like 10 to the 9 and 10 to the 12 GeV or so. So these are kind of heavier neutrinos. And of course, this is the lightest one, so the other ones are even heavier. So it's not a nicely detectable model, right? It's, 10 to the 12 GeV, 10 to the 9 GeV is even 10 to the 9 GeV is very high, so you cannot look for these particles at the LHC. So this is the most basic leptogenesis model. There are many other versions of leptogenesis, and especially there are models called resonant leptogenesis models, which work at which work at lower scales. So there's resonant leptogenesis. This is by Plusses and company. Leptogenesis. Leptogenesis, yeah. So resonant leptogenesis scenarios work at lower scales, or there's also, there's also a kind of low-scale leptogenesis. So this can work with right-handed neutrinos that are a TV scale or maybe a bit heavier, which is nice because those are the LHC scales. So especially for the resonant abiogenesis case, you have two states. So two of your neutrinos are almost degenerate, so there's a very small mass difference, and the CP violation goes like, I guess, some mass scale square over delta m, basically, delta m square. So you get a resonant enhancement from the small mass differences. That's why you can lower the mass of the right-handed neutrinos. It's not, but then you need to be careful if you are still explaining the neutrino masses or not, because you still need at least two neutrinos to make at least two of our neutrinos massive and also very light. So you need to add an extra neutrino basically here. What other leptogenesis models? Oh, another thing that I want to say about leptogenesis is that, again, we only, my biggest assumption was that I'm only interested in the right-handed neutrino decay, and it decays to our leptons, right? You really need to include the scatterings as well, because those are also lepton number changing, right? So you need to include all interactions that change lepton number, and that will be changing lepton number by 2. You are going from an L equals 1 state to an L equals -1 state, so you are changing lepton number by 2. And also, you are here, all of your decays are kind of flavor dependent, and when you are decaying into neutrinos, neutrinos also oscillate between flavors, and sometimes one of the flavors will freeze out maybe before the other ones, and then you need to also include neutrino stations and stuff, and the interaction of each flavor with the standard model plasma as well. So if you read any Leptogenesis paper, you will see that the Boltzmann equations involved in Leptogenesis models that you need to solve to find the final asymmetry is actually extremely complicated and very long. And there are also mathematical codes that do this for you, which is nice of the people that write those mathematical codes. Okay, so this is what I wanted to say about Leptogenesis. Again, I did the easiest version. The complicated versions are a lot more complicated. So in the next lecture, tomorrow's lecture, I will finally talk about baryogenesis, electroweak baryogenesis. And if I have time, I will talk about spontaneous baryogenesis as well.